Have you ever stopped and wondered, how on earth do we take the temperature of, well, the entire Earth? I mean, you can't just stick a giant thermometer into a mountain, right? Or dip one in every single river. The scale is just massive. But the answer, believe it or not, is way up there, an eye in the sky. So let's dive into how it's all done. All right, let's start with a puzzle. Just look at this incredible landscape. How would you, you, measure the temperature of this entire mountain range all at once? I'm talking from that snowy peak way up high all the way down to the warmest spot in the valley. How do you get that single snapshot? Well, the answer is hundreds of miles above us. We're talking about satellites, of course. Orbiting way over our heads, they're basically our planet's super high-tech thermometers. But here's the twist. What they see isn't just a number on a display. Nope, it's a really complex signal. Kind of like a secret code that needs a whole lot of translation before it makes any sense to us. So that brings us to the first leg of our journey, a planet's temperature check. Let's figure out what these satellites are actually looking at. Okay, so this is probably the most important thing to get your head around. Satellites don't actually see temperature. It's not like they're looking down and seeing 15 degrees Celsius. What they're really seeing is just a raw digital signal, a long stream of numbers. And our job, our challenge, is to decode that stream of numbers and turn it into something meaningful, something we can actually understand. So, where do we even begin with that decoding process? Well, the very first step is to take that raw signal, clean it up, and convert it into something called radiance. This is our first major transformation. You know, one of the biggest hurdles right off the bat is the Earth's atmosphere itself. It totally gets in the way. The satellite isn't just seeing the ground, it's looking through all this stuff. Dust, haze, water vapor, you name it. It's all just scattering that thermal signal. Think of it like trying to look through a really dirty, foggy window. Before you can see what's outside, you gotta clean the glass. And wow, look at the difference that makes. Seriously, on the left, you've got that original, hazy, messy signal. But on the right, that's after we apply a pretty cool technique called Dark Object Subtraction. It's so much clearer, right? We've essentially just wiped that dirty window clean and filtered out all that atmospheric noise so the real signal from the ground can finally come through loud and clear. So what we're left with now is something called top of atmosphere radiance, or TOA radiance for short. Now, this isn't just a random string of numbers anymore. This is a real, calibrated measurement of energy. The energy that actually left the Earth's surface and made it all the way up to the satellite. We are one giant step closer to getting that temperature reading. And here's what that looks like as a map. This is our TOA radiance map. You can see those bright yellow spots? That's where more energy is being radiated. The darker reddish areas are radiating less. It's really starting to look like a temperature map, isn't it? But hold on, we're not quite there yet. Okay, next up, focusing the satellite's view. Before we get any deeper, we need to kind of zoom in. A full satellite image covers a huge amount of territory, way too much for a detailed analysis. So we need to isolate the one specific area we really care about. So how do we do that? Well, first we have to make sure all our data layers line up perfectly. We reproject the data and then essentially use digital scissors to clip out just our region of interest. This is absolutely critical because it means every piece of information we add from here on out will line up perfectly, right down to the individual pixel. And there you have it. We basically just cut out everything else, leaving only our target valley. Now our analysis is focused, it's manageable, and it's super precise. All right, this is the moment we've all been building up to. It's time to go from radiance to temperature. We're going to take this clean, focused map of energy and finally turn it into a temperature reading. Okay, so using some pretty standard physics, we can convert that radiance into something called brightness temperature. But, and this is a huge but, there's a catch. This calculation makes one big assumption. It assumes that every single surface on the ground radiates heat perfectly, like an ideal black body from a physics textbook. And we all know the real world just doesn't work that way. And here it is, our very first look at temperature. You can clearly see the colder spots in blue and the warmer areas in red. It's a massive step forward for sure, but it's not the whole story. It's not totally accurate yet. So what's missing? Well, think about it. A forest just doesn't radiate heat the same way a field of snow does, or a patch of farmland. We have to figure out a way to account for what's actually on the ground. And that brings us to the final and maybe the most critical piece of this entire puzzle, the emissivity factor. This is how we correct for all those different types of surfaces. So what is emissivity? It's basically just a score, a number between 0 and 1 that tells us how good a surface is at radiating heat. The perfect example is a black car versus a white car on a sunny day. The black car gets way hotter, right? That's because it absorbs and radiates energy much more efficiently. It has a higher emissivity. And all the different surfaces on Earth, water, rock, trees, snow, they all behave in the same way. So to apply this correction, we need another layer of data. We need to know what we're actually looking at. And that's where this comes in, a land use land cover map, or LULC. It's pretty straightforward. It just identifies what's on the ground. So you can see here, green represents forest, gray is snow, yellow is cropland. You get the idea. And here's why that map is so important. Each of those different land types has a known emissivity value. Take snow, for instance. It's actually not great at radiating heat, so it has a lower value, 0.82. But a forest or a field of crops, they're super efficient, with values almost at a perfect 1. So by taking these specific correction numbers and applying them to every single pixel in our image, we can finally calculate the true accurate temperature.
So let's recap. We've taken the raw signal, cleaned off the atmospheric haze, converted it to radiance, made a first pass at temperature, and then corrected it for what's actually on the ground using emissivity. After all that, we are finally ready to see the final product. And there it is, the final temperature map. This is the real deal, a scientifically accurate map of the land's surface temperature in degrees Celsius. You can see it plain as day. The cold, snow-covered peaks are in deep blue, and the warmer valleys and lower elevations pop out in red. Every single one of those tiny pixels represents a precise corrected temperature measurement. And now we have actual hard data. In this particular spot, the hottest temperature we found was 10.8 degrees Celsius. How cool is that? We've successfully traveled all the way from a meaningless stream of numbers beamed from space to a real, tangible measurement right here on the ground.
And all of this leaves us with one final big question. I mean, this whole incredible process, it allows us to see so much. We can spot urban heat islands in cities. We can monitor the health of crops to predict droughts. We can track how fast glaciers are melting with unbelievable precision. So if this map can reveal so much about what's happening in just one small valley, just think about it. What could it tell us about the health of our entire planet?